Thanks. So I'm just going to talk about a LunaH-Map mission. It's another one of the Artemis 1 CubeSats that launched last year. If you go to the next slide. This was the spacecraft when we integrated into the OSA in July of 2021, and that's me removing the last remove before flight plug before they closed the door on the dispenser. But just to give you a sense for the size of the spacecraft, that's the back side of the spacecraft on the left, and the neutron detector, which is our one science instrument, is on the other side of the Z face of the spacecraft, pointing away from you. And that's what I'll be talking about in terms of the data that we collected from the mission. If you go to the next slide. These are all the subsystems on the spacecraft. The neutron spectrometer is shown on the far left. It's an array of 4 scintillators in 2 detectors. So there's 8 scintillators total, which detect both neutrons and gamma rays from planetary surfaces. And when you get close enough to the moon, we can pick up signals from neutrons and gamma rays that are emitted from or generated from the lunar surface. And those are the other subsystems on the spacecraft. As well as one of the important things we generated from this mission is stood up a mission operations center at ASU in partnership with some small commercial companies in the Phoenix area, both Kinetics and Qualtech, which have a lot of experience on deep space missions, both operations and navigation. They've been critical for us to keep the spacecraft operational for the 6 months after launch. If you go to the next slide. And one thing I should mention on the last slide, you see the propulsion system. We use a Bit 3 is a iodine-based low thrust propulsion system, and I'll talk more about that in a future slide. But this is us in the OSA with the other 10 Artemis or other 9 Artemis CubeSats. And if you go to the next slide. Our primary science mission was to map the ice distribution within and outside of permanently shadowed regions at the south pole of the moon. This just shows the intention for the mission was to use our small propulsion system to get into a low altitude south pole orbit where we could get close enough to these PSRs to determine if the ice is contained within the PSRs or actually extends into the shallow subsurface of the moon in partially or fully illuminated regions outside of PSRs. And so one of the key components of a neutron detector is that it's sensitive down to a meter below the lunar surface, and so we can tell something about the bulk ice distribution both within and outside of PSRs. And so this shows one ground track over Shoemaker. The contribution from the PSR to the neutron detector gets up to almost 80%, which is really fantastic at this low altitude, which you can see on the bottom right, getting down to just about 10 to 12 kilometers over the lunar surface. And the intention was to do this about 300 times and generate a map of the entire South Pole hydrogen distribution. If you go to the next slide. That should show a prediction map. So based on the distributions of ice or hydrogen that are shown on the left, LunaH-Map would be able to reconstruct the map on the right, which shows that we would be able to discern one permanently shadowed region from another. So go to the next slide. This is the ops team after launch, just looking for our first piece of telemetry, which arrived around 9:40 a.m. Go to the next slide. And so this is where we're at. We did successfully achieve the ability to collect neutron data on November 21st throughout our flyby. We also demonstrated an onboard auto navigation demonstration with our team at Kinetics to show that these types of spacecraft can steer themselves in the future, which is going to be really important with minimal DSN resources. And we're unlikely or very unlikely at this point to achieve any low altitude neutron measurements of the South Pole. And we attempted several times to conduct a new type of ranging demonstration, but I've heard that some of the other cubes were able to do that. So that's great. Go to the next slide. This is more on our mission status. We were unable to ignite the propulsion system. Similar to BioSentinel, the long delay between spacecraft delivery and launch didn't really help us very much. So in our case, we were aware of an issue with the iodine vaporizing and getting bound up into the valves and other components in the propulsion system after a long wait in ambient conditions. And so there was really nothing we could do in terms of getting the spacecraft back to declog the valves. So we tried to heat the system up. That's what we've been doing since launch. to try to heat up the iodine and vaporize more off and increase the pressure in the system to try to actually unstick the valve. And we've so far been unsuccessful. So we will plan to declare an end of our mission May 31st. Go to the next slide. So the good news is we did collect science data. If you go to the next slide. I can blaze through these just to show you guys. This is the ground tracks. We collected 5 sets of science data, 20 to 30 minutes in duration. There's the maps that we would be able to make. Those circles that you see there are the pixel sizes, the effective pixel sizes for the 3 pixels that we would be able to generate over the Mare and Highlands. If you go to the next slide. These are the data, some of the data that we collected from one of the modules. In the circle in the bottom, you can see the lunar neutrons lighting up as we came to closest approach and then going away at departure. If you go to the next slide. This should be an animated GIF showing for the modules that were closest to the moon. We can see them increasing the neutron signal and decreasing as we go away from the moon. If you go to the next one. This is our orientation. So we had to decouple the orientation effects from the geometry of the moon and with respect to the spacecraft and detectors. If you just go through the next few, you can see in the upper right the detector orientation. Just keep going. This shows how the orientation of the spacecraft was used. And this is the models that we use to understand the data and turn it into a hydrogen content. It predicts what we would see with the spacecraft, which was with the instrument, which shows the instrument did work as expected. And would be able to conduct and complete our science mission. You go to the next slide. I think it should be the last one. Oh, this is the star tracker. So this is pictures of Uranus and a constellation that we use to demonstrate the onboard auto navigation. If you go to the next one. This is where we'll end up in 2039, back about 27 lunar radii away from the moon. And we're in a sun and heliocentric orbit. Keep going. These are just all the things we demonstrated on the mission, and I just wanted to point out that these are a really important thing to consider for future Artemis launches as well as future lunar exploration. We were selected to provide the neutron and gamma ray spectrometer for the LunarVise mission, which is going to be based on the LunaH-Map neutron detector, and we're using the gamma ray capability as well as the neutron capability to accomplish the science goals for that mission at the Gruithuisen domes. So these are really important technology demonstration missions as well as proving grounds for new students and companies and PIs and really increasing diversity of mission participation. So I really hope that for future lunar exploration, we consider these very, very small science investigations as we move forward. Thanks a lot.